Hey, what is going on? Today we are going to do a Leetcode problem as usual. Welcome to Coding with Shaf, where I try to daily do a Leetcode problem video just to get the coding juices flowing. They're always good to keep you sharp for interviews and just so you can kind of use your brain and always say that you coded maybe at least an hour a day or however long it takes you to do some of these challenges. So yes, with that uh, preamble, it's February 24th, Thursday, 2022. Um, I am going to tackle the daily problem, the daily challenge. All right, and the daily challenge is called it's Leetcode 165. Compare version numbers. It's medium. There's a lot of more thumbs down than thumbs up. Just looking at the problem, I think I can figure out why, but let's just go over the problem. Okay, so this problem is I think it's pretty straightforward actually. And we have given two version numbers, version 1 and version 2, compare them. Version numbers consist of one or more revisions joined by a dot, so the semantic versioning paradigm. Each revision consists of digits and may contain leading zeros. Every revision contains at least one character. Revisions are zero indexed from left to right, with the leftmost revision being revision 0 and the next revision being revision 1, and so on. For example, 2.5.33 and 0.1 are valid version numbers. Okay, so you've seen those version numbers before. To compare version numbers, compare their revisions from left to right order. Revisions are compared using their integer values, ignoring any leading zeros. This means that revisions 1 and 001 are considered equal. If a version number does not specify a revision at an index, treat the revision as 0. For example, version 1.0 is less than revision 1.1 because their revision zeros are the same, but the revision 1s are 0 and 1 respectively, and 0 is less than 1. Okay, so this is kind of like writing a comparator for versions. Okay, where version 1 is less than version 2, we have -1, right? And for version 1 greater than version 2, we have 1. So version 1 is the left operand. Um, Otherwise, return 0 if they're equal. And so you can look at kind of these examples, I think, and just see, like, you can imagine that there's a bunch of like potential edge cases. This is one of those problems where you gotta, I think, keep track of the edge cases. Right, there's a lot of problems on Leetcode that look simple, but the edge cases that can definitely trip a person up and make the code kind of bloat with a bunch of additional cases. And ideally, in like interview situations, they, at least from my experience, they do kind of sometimes give problems that have a lot of edge case behavior just to see if you're nuanced enough to kind of be aware and track all those edge cases. But lots of times, you have like more pure data structures problem that has your understanding of a specific data structure slash data structures, and these edge case problems are not what appear. So I guess it could be a mix, but these are good practice anyway, just to make sure you can build your awareness of edge case behavior. And I'm assuming too, this looks pretty straightforward to me anyway. So let's see, what do we do here? So first we want to do, first thing we want to do is we want to split these versions into their parts, their major, minor, and patch. Okay, so one thing we got to note that some versions, when we compare version numbers, the little tiny tricky part is that some might not contain all the parts the other version might. So you have to take that into account. So what does that mean? So that means that these two are equal because the leading zeros also have to be taken into account. So this is 1.1, this is 1.1 for all intents and purposes. But in this case, these are also equal because this is 1.0 and this is 1.0.0. So you have to kind of keep track of how far you've gone already to the right. And this is 0.1 and this is 1.1. And even though they have the major and minor both, comparing the majors, you already see that the major of the second version is smaller than the major of the first. So you can kind of like end the iteration right there. And that's, I think, the quote trick unquote is like you can kind of end the iteration before you have to start detecting all edge cases down to smaller patch numbers. So as I was saying, I think the first thing we want to do is we want to split the strings into their various parts. So that's what I'm going to do. Parts1 equals version1 dot split. So this is, you're splitting by escape character, right? So in order to split by a period, right, special character, because in regex a period has a special meaning. So you want to split not by the regex character. You want to split by the actual period. So I should turn autocomplete off for these to make it more challenging. No, okay, so we now have the different parts of our semantic versions, right? So they're split into the different, like 1.0.1 is split into an array of 1.0, 1, 0, and 1, right? Character strings, and that's a 3 size, an array of length 3, and parts 2 is a array of length 1. So that's another thing we have to consider, because you can imagine we're going to iterate through this array. So we will have to kind of figure out how far we want. We need to kind of compare left to right simultaneously. That kind of makes it easy, but we have to know that left and right are not always going to be the same length in terms of the size of the parts arrays of each version. So what we need to do is, in our loop, so I'm going to make a for loop, I'm going to iterate simultaneously, right? Parts1 dot length, or I is less than parts2 dot length. Okay, why am I doing this? Because I'm simply iterating through both of these arrays simultaneously, and the or condition makes sure that I can get to the longest length, right? So now you're thinking, I mean, you probably know, but some people might be thinking, what if I go too far out past the bounds of one array, right? So that's what we're going to leverage, the fact that these arrays may be different. So first thing we're going to do is count for the situation where we're in the same part, semantic versioning part, and I'll show you the condition. I is less than parts2 dot length. Okay, so this is basically saying, get out of here. This is basically saying that while both are below the max length of either of these, right? While the iterator is below the max length because it's got to be less than both parts1 length and parts2 length, then do something else. If it's less than parts1 dot length, do something else. If I is less than parts2 dot length, do something. So this is like something just to get used to, right? Like now we know that if we're less than parts1 dot length, right, then the first condition catches when we're below both. The second condition catches when we're below parts1 dot length, but we're not below parts2 dot length, right? Because that means parts1 is longer than parts2, right? And we've gone outside the bounds of parts2. Or the last condition is if the I iterator is below parts2 dot length. That means parts2 is longer than parts1, and we've gone outside the length of parts1, right? So we need to capture all those things. And by the way, I believe, let's just double check where we are. Okay, our return value, remember, at the end of the day, I want my loop to kind of iterate, and if there's no difference by the time the iteration ends, I want the loop to return 0, meaning the two versions are equal. So that's how I feel this is going to work best. So let's see. First thing we want to do is now we can use the built-in function, Java function. I'm using Java here. To parse the integers, right? So I'm going to create two integers from each part of the semantic version array. Equals integer dot parse int parts2. So this is something a little nuanced, but what you need to know, it's not really nuanced, but it's something you should just be aware of. These versions, these parts, it's specified, I believe, that these are numeric, right? Can be stored numeric, and numeric are digits, consists of all digits with the possibility of leading zeros. If we had a situation where we had a non-alphanumeric or non-numeric possibilities, then we couldn't just simply do this. In fact, we couldn't just simply compare the two together. We'd have to understand how we can create an ordering between the two versions, right? What the alphabetic versions mean, and we couldn't do this parse int without catching this uh, catching an exception, the number format exception, because it may not be an integer in here. So that's something to just keep in mind. But this problem is simplified that way. So this is what I'm going to do. If v2 is less than greater than return 1, right? Else, if v1 is less than v2, return -1. Okay, so in this condition, I'm checking whether v1 is greater than v2. And if that's the case, that's according to the rules that were specified in the input, right? Here, okay? Version 1 less than version 2, return -1. Version 1 greater than version 2, return -1. And I'm not going to use look check equality here, because if these are equal, we're not going to do anything. We're just going to move to the next iteration. But remember, these are in order from left to right. So that's actually pretty nice, because if you have a digit that's greater than the other, then you know right away that you don't have to check any of the other parts. Okay, you can just call it a day there with your loop, and that's it. But in the event that now we have gone past the boundary. Now we've gone past the boundary of one of the semantic versions. Let's say parts 2, right? So now what we're going to do, we're going to parse again parts 1 I, and at this point we're going to do a check here. v1 not equal to 0, return 1. Okay, so here at this point we have nothing to compare. The only thing we can do is be greater, because if you look at the semantic versions, if we are outside, let's take this guy, if we're outside the parts length, we can't compare, right, anything with the parts from 2, because there's no parts left. So we can't be less at that point, right? The only thing we can do is be equal or greater. So if you parse out a 0, then at that point, as long as you're iterating, you're still equal. If you parse out a 1, then you're automatically greater. There's no negative versioning here in semantic version, or at least we haven't specified for this problem. If that was the case, then we'd have to change again this problem, and we'd have to modify this condition check, but luckily that's not the case. Integer.parse int parts 2. So similarly, I am doing the same thing here in this conditional, because this is a symmetric type of condition, because we're outside of the parts 1 boundary. And now, since we're outside of the parts 1 boundary, we can apply the same check to parts 2 and see if we've got a version part that's larger. So this is what I think the code is. I think, let's try running it. This is accepted. And we can do the checks for the edge cases. Specifically, you got to check leading zeros, right? Right. That's always important. So that's accepted. And then I think, this is the case where, and remember, this could get tricky because there's many combinations potentially of version geometry, as I call it, and that's correct. So let's try running it. And there you go. Faster than 90% of submissions. Pretty good. Space is not that great, but hey, I look at the O1 right now. So we could have probably reduced the space somehow, maybe without even splitting, and just doing character and integer comparisons. But hey, that's what it is. All right, so that's the problem for today. And if you like this video, like, subscribe, and leave a comment below. And I will see you next time. Bye-bye.